la última charla del curso de pruebas asistidas por computadora. Una vez más, Jean Philippe Lessard de la Universidad de McGill. So thank you, Jean Philippe.
Thank you, Renato. So it's a pleasure to be here for one last time. I'm glad to see that many of you guys stayed. That's impressive. So basically I'm too tired to write anything on the board at this point, so I'm just going to show you some results and some applications, and going to talk about the methods, but essentially you've seen everything. So, you know, I'm so shallow, there's nothing else I can talk about, so I'm just going to talk about some applications and results, okay? So the first, so Jay talked a lot about the circular restricted four-body problem, and thanks to Jaime, then we actually started to work on that, and we've worked quite a bit. In fact, Jaime made me work a lot to try to apply these techniques to this problem, but we have succeeded in proving the existence of many of them. So, well, these are the equations of motions for one particle, which is, moving in a central around the central configuration, which is an equilateral triangle, and the masses are here. So that's the picture that you've seen. I think it's already the third time that you've seen that picture. So basically now what I'm going to talk about is basically proving the existence of periodic orbits in that setup, and not only the planar ones, but the spatial orbits. So I'm going to show you some pictures, and I'm going to talk a little bit about the techniques that we use. But as I said, you heard most of the techniques up to now. So that's the lemma, and don't read it. All it says is that there is a nice way to rewrite the circular restricted four-body problem using the tricks that Jay talked about of automatic differentiation. So basically, we rewrite by introducing three more variables, which are taking care of the square roots at the bottom here. So that's the nonlinearity here. So basically, we introduce U7 to be R1, U8 to be R2, and U9 to be R3. Did I say, okay. Yes. So these three extra variables, they satisfy a simple differential equation. And basically these simple differential equations are here. So now we have a new polynomial vector field, which is, so we started with 3 second order ODEs that became a 6 dimensional first order ODE, and now it is a 9 dimensional polynomial vector field. And that lemma, what it says is that we have to introduce some unfolding parameters in order to be able to apply our contraction mapping theorem. So what this is saying here is that I have 1 unfolding, 2 and 3, 4 unfolding parameters. So what this is saying is that assume that you can find a periodic solution to that problem with the unfolding parameters in the equations. And assume on top of that we have a Poincaré phase condition which is satisfied, and that we have that the 3 extra equations that we appended at time t is equal to 0, they satisfy these relations. Basically, it's saying that we're not solving a different initial value problem, okay? So if we can find a periodic orbit of that problem, and if on top of that we can verify simultaneously these 4 extra equations, then we can construct, okay, so first we have that all the unfolding parameters are 0, and that's due to the fact that we are looking for a periodic orbit. So if they were not equal to 0, we have proofs that would lead to a contradiction of having a periodic orbit. And after that, we can recover the solution. So the first 6 solutions of that ODE, then they provide periodic solution of the circular restricted four-body problem. Okay, so that basically now, that's the problem we're going to solve. And some of the orbit, as you will see now, in fact, are pretty long and pretty big, because if you look, okay, this is not maybe so clear, but these are the 3 primaries, and then these are all on top of one another, the proof that we did, the computer-assisted proofs. So these orbits, say, for instance, for the halo orbit, you can see that the amplitude is really, really big. So these are kind of long orbits. And we tried to apply Fourier, and things were not working so well. These were difficult orbits. There were many bifurcations, so sometimes, I would start trying to prove a solution close to a bifurcation without knowing it, because I don't know anything about celestial mechanics, so I was just trying to apply my tricks over and over without really going deep. But then Jay was nice enough to actually figure out that there was a bifurcation close by one of the first orbit I was trying to prove, and then we moved away. But in this process, in this struggle, we actually decided to do Chebyshev expansions of the solution. So basically what we did was to to, instead of doing one Fourier to express the solutions, we took domain decomposition in time, and then we glued all the small little pieces, so that what you really see here is like, I think for all of these proofs, I used 10 domain in Chebyshev. So basically, this is like a segment of 10 subdomains. And because of that, then the decay rate was much faster. So if you think of one Fourier expansion for each of the components, then since that's a large orbit, and on top of that there are singularities around, so the decay rate is not so quick, and that means that I don't have a lot of room for this my weight nu in my L nu1 space to do the proofs, and sometimes to take nu larger is very helpful in order to have a contraction. So because of that, then we moved away from Fourier and we applied Chebyshev expansions piecewise, and that turned out to be working quite well. There was still some instability with the fact that we were using FFT and interval arithmetic, but we figured out some tricks, and then basically these are all now proofs. And the projection dimensions, for instance, for these halo orbits, so these halo orbits are bifurcating from one of the primary, which is it? Yeah, which one? This one, okay, anyway, yeah, so out of L6, there are Lyapunov orbits which are growing out of L6, and then there are off-plane bifurcations, and these are the halo orbits. And the fun fact is that the next generation telescope, the James Webb telescope, is going to orbit in one of these halo orbits, not in the three-body problem, in the four-body problem, but in the three-body problem. And then the home of the telescope will be one of these halo orbits. So that's kind of a fun fact. Okay, so these are computer-assisted proofs, and then, as I said, so the largest orbit here, so the projection dimension, including all the Fourier, all the Chebyshev coefficients for each subdomain, and each is a 9-dimensional function. So function in R9. So it's basically that's a lot of Chebyshev coefficients, right? So the largest one is the total projection is 1,606. It's not so large for modern computers, but that's still not so small. Yes.
What are those dots that look like stars?
The primaries.
Oh,
the primaries.
I put a starry background.
Ah, yes. So that's Jay who had fun. Okay.
Non-mathematical.
Sometimes we just get, you just need to have fun, right? But yeah, these are the primaries, and then. No. That would have been nice to prove all of these dots. Yes. In fact, yeah, these are massless guys because they do not influence the movement. These are all massless stars. We're so serious. Yeah. We're so serious researchers. Okay, so that's the halo orbit. So we have different type of Lyapunov families, but spatial ones. So these are, again, periodic orbits which are growing out of some planar orbits, and then there are some off-plane bifurcation. And so that's from the top, and that's from the side. So you can see that their amplitudes are extremely large. So again, in that case, we had to go for the tallest one. We had to go all the way to 2,614 coefficients to do the proofs. What you see in these tables basically are the R's for the polynomial, the smallest R. So let's say the smallest R that we have is 10 to the minus 12, and goes all the way to 10 to the minus 9, 10 to the minus 10. So these are basically as we showed, C0 bound, yeah, as we showed in the first date, and these are C0 bounds for the orbits. And if we wanted, we could have
2,600 coefficients in each domain?
No, in total. That's the total projection. No. In fact, for each domain, it was not so bad.
So probably how many domains are we talking about? 10?
Yes, 10 domains.
10 domains.
And then they're all, 10 domains, and then each, these are not two-sided. The Chebyshev, there are one-sided sequences, but then to compute the convolutions, they're two-sided. But you have to take that, you divide that by 10, so it's in average 261 per domain divided by 9, because then you have, so we can count it. I'm too tired. I can't compute 261 divided by 9. Anyway, so that's the total projection. But that can go high quite quickly. But the thing is that because of the decay rate on each domain of the Chebyshev, then that was really beautiful and working. And the periods go from 4 to 8. So the longest period here is 8.88 something. Yeah. Okay, and these are other type of families. So all of these are ones that appeared in this gigantic mess here. And then since there's symmetry, then so this is at equal masses, I have to say. So because of the symmetry, then they appear, so when we do, out of this one, there's another family, and there's yet another family. So we get 3 times this for free somewhere else in the in the phase space. Okay, and then, so that's one last one. So these are kind of cute because they actually go, I mean, that's the one which is kind of close to the plane. So it goes at the back and comes back and goes up and then comes back at the back and closes. So, and these are also really big because they are completely, I mean, kind of, if you look from the top, they're really completely surrounding the primary. So these are gigantic periodic orbits. Okay, and in the phase space, and the errors, they go from 10 to the minus 13 to 10 to the minus 12, and again, the largest dimension for the say the hardest proof was about 2,600. Yeah. Okay, so I'm not going to tell you more in terms of the techniques. It's basically finite dimensional projection. You take the numerics, you center it in a ball, but now it's going to be cross products because we're going to have basically 9 times the number of domains copies of L nu 1, and in that case L nu 1 is going to be corresponding to Chebyshev coefficients, and that's a Banach algebra under discrete convolution. So all the nice tricks that we talked about, but basically it is 9 times 10, so it's about 90 copies of L nu 1. So there's a lot of and then on that space, and we introduce the max of all the L nu 1 norms, and then that's our Banach space. And we have the unfolding parameter, so that's basically R4 cross L nu 1 to the power 90. So that's our Banach space. And we apply Newton to a finite dimensional projection, we converge. We got the data from Jaime, who actually did a lot of that first by integrating the equations. And we took that, we kind of moved these data to Chebyshev space, and then we applied a Newton, and then we proved that nearby the approximate solution, there was through solution for each of these computations, and then again using this A dagger the bounds of Y0. It's all in the same spirit. Okay, so these are, these are kind of nice pictures. And just so that you see the profile in time, so that would be one of the halo orbit, and we also did proofs at non-equal masses, and that at non-equal masses, in that case 0.5, 0.3, 0.2, so that's one halo orbit, and what you can see here are the profiles of the 9 components. So basically, again, for this kind of orbit, then we subdivided in 10 subdomains, and then each was computed using Chebyshev. And that's another one. It's the axial family. It's also a spatial orbit, and then you can see their coefficient, their profile here. Okay, but again, exactly the same ideas. Okay, so as I said at this point, I'm just going to put different results on the board on the slides. And so that was that's a little bit older, this result, these proofs. And that's joint work with Rafael de la Llave and Jordi Luis Figueras from Uppsala. So so that's a PDE. That's a very popular PDE, in fact, to understand, in my field, then we are interested in proving some results for Navier-Stokes, but that's hard, right? I'm going to talk about Navier-Stokes a bit later, but that's kind of a baby version to try to understand very complicated dynamics in a PDE. So that's a fourth order linear term in U, and that's U sub t. So that really gives rise to a semi-group. That's a dynamical system. It's dissipative, and there are proofs that the global attractor is finite dimensional. And so because of that, then when you actually decrease the parameter nu, then you get more and more complicated dynamics, and that's what we're after. We're trying to get proofs of different type of dynamical object for that PDE. Okay, so I'm going to show you some theorems. And so what is the idea here? So the idea is that we have a PDE which is, in that case, defined on one-dimensional domain. It's periodic boundary condition with some odd boundary condition, so that in space we can use signs, and in time we can use. We used Fourier expansion in time, so it's basically a Fourier expansion. And the fact is that this is the linear part, and in Fourier this is nicely diagonal. Okay, so that's kind of the idea that once you move to Fourier in time, Fourier in space, because of the shape of the linear part, then that leads to a nice diagonal dominant It needs, I mean, sometimes we need to work way more in order to get the diagonal dominance, so we have to compute more to get it at some point. The linear part becomes, I mean, give us enough contraction. I mean, if you go back to Jay's talk, then you know you had a 1 over n there. It's basically because you were taking a derivative. So for us, the more derivatives we have, in some sense, the more contraction we get. So it is kind of easier. That's why sometimes we are interested even in modifying the original equation to differentiate a little bit more, to get more regularity to get more contraction from the proofs. But we didn't do that here. Okay, so the idea is to plug a Fourier series, space-time in the equation, as usual. I mean, now you're probably getting bored of this. I mean, I could have taken a Fourier expansion, plug it in there, and then get a map to solve in the space of Fourier coefficients. Now, these are infinite dimensional matrices of Fourier coefficients. So these are my Fourier vectors, and then now I'm solving in a weighted L1 space. Now in what? In the same norm, and because again of the fact that these solutions they exist for all time, then they're very smooth, so they're very regular. So we can take L nu 1 with some geometric rate. Okay, so that's what we did. So these are this is a proof here, and then we took a parameter value in the chaotic regime. Well, yeah, it actually was proven recently by Piotr Skliczynski and Daniel Wilczak using computer-assisted proof that there was symbolic dynamics in the Kuramoto-Shivashinsky equation. So I can now talk about, well, I cannot talk about characterization of the global attractor, but they prove that there is some symbolic dynamics there. And this is in the chaotic regime, then that's a periodic orbit. So for this, we had to take, and the total dimension was about 32,000. So that, I mean, Marcio is quite a well-educated programmer, and we did all of that in C++, and he needed to do some tricks in order to get memory efficiency. So for me, for my computer, for this guy, that starts to be difficult. So we did that in Marcio's office in San Carlos. And okay, so what is this orbit? So this is in space. So basically, you can think of this as the initial condition, and you go all the way back to yourself as you move in time here. In this direction. So the period for that guy is about 0.53, and the C0 bound is 10 to the minus 10 that we get. And what we have is that we also prove the existence. So once we did the proof of the periodic orbit, we linearized the equation and we computed one positive Floquet multiplier. And in that case, that led to, that means that this solution is unstable. So we actually have a proof that this is an unstable periodic orbit. And by computing the eigenvalue problem, we computed the eigenvector, and then the eigenvector gave us basically the stable manifold is tangent to that, and this is a picture of of three Fourier modes of the orbit, because Fourier mode as a function of time, because when we write in Fourier, we can write it as a coefficients that depends on times sign in space, and these coefficients that depend on time, then we still do a Fourier expansion, but these are, say, I think the 7, 8, and 9 time-dependent Fourier mode in space, and well, that creates quite a nice picture. And what you see there is the tangent bundle, as the tangent bundle associated to the well, I say tangent. It's like a normal to the orbit, but it's the unstable manifold is tangent to it. And what you see there is just locally the unstable bundle. Yes.
How do you guess this? You need to have some guess.
Yes, so there is. So in that case, I did simulations, because this is there's a global attractor. So I did some integration, and I asked my computer when I was getting close to close myself, to get close to the solution in the function space. Then I was applying the FFT, and I was applying Newton to try to see if I could converge. So I did that for a bunch of them. And you're right that this is okay. You're right that this one didn't really work, but still. It's in the attractor, so basically, even if it's unstable, at some point you just recover something. Yeah. And it's just I did not. Yeah, I mean, if I was really trying to start close to it and stay close to it, I would get away from it. Yeah. So that's how. So that's pretty neat, and that leads to some nice pictures. I like it. And that's another one here. So this one, the period is 0.89. And again, we showed the existence of a positive real Floquet multiplier. So in that case, 1.33. So it's also unstable. And for this one, we used 40,000 as the projection. Actually, that's not true. The projection, the numerical projection was 7,822, but that was the matrix we needed to invert in order for the proof to carry, I mean, to go through. And in fact, what I mentioned before is that the linear part is very important, but it's giving me a contraction if I take enough modes. So there's kind of an idea here that we compute some finite dimensional approximation, but we still need to invert a matrix of a bigger size in order for that eventually to become a contraction, because that's actually not a lot, right? This is only giving me a 1/k in Fourier. So because of that, we had to invert large matrices, yes.
So this is a question of inertial manifold or something like
I
that.
think, I mean, people have written papers about it, like gazillions of papers. But I'm not an expert on that. I know that some people treat that as a, way to actually get a finite dimensional ODE, and then but it's not clear to me how to actually do proofs using the inertial manifold. I mean, there's like this idea of Lyapunov-Perron kind of operator, and you need to get your hands on it. And then from our point of view, it's at least, I've been thinking about this a little bit with I think it was a student of Mike Joly, I'm not sure, and who's been working on this equation for a while. And at least from my perspective, it's not clear how to use that to get proofs. I mean, yeah. Okay, and yet another one here. So that's nice because when you look at this, then there is a Floquet multiplier, which is giving rise to a Mobius strip. So this one, again, is unstable. So we can see the unstable bundle, but then the unstable bundle, there is actually a Mobius strip. There is rotation. So there's a lot of nice type of orbits there. And that's also a proof. The C0 bound for this one. So 10 to the minus 11 close to that orbit, then there is a true orbit for Kuryabon-Tuchyshevsky. Okay, and that's a very long one. In fact, that's the period here is more than 20. And well, yeah, we have an initial condition, and then it kind of shifts at some point and it continues. And for this, the numerical data was about 10,000, and we had to invert a big matrix of size 40,000. Okay, so another application, but this application I find it very interesting because that goes back to what I was talking about yesterday in terms of not having to care about the environment surrounding the orbit. So that's a case where we have, it's like the UTT equals UYY plus fourth order term plus a quadratic term. And in that case, it's ill-posed. People call it the bad version, but the physicists call it the good version because that's the one which is supposed to represent a study of water waves when the water is pretty shallow. And so it was in fact proposed by Raphael de la Llave the group organized a workshop in Palo Alto back in the days. And so some mathematicians were invited just to give us open problem, and that was the open problem of Raphael de la Llave. So then from our perspective, it was pretty natural to just apply Fourier analysis to it and not having to care at all about the outside world. So basically, once you plug a Fourier expansion in this, you forget about everything else, even though these are solutions here. So close to that solution in the function space, there's no well-posed initial value problem. Whereas if you're exactly on it, then you do have, the existence of solutions for all time. So from our perspective, it's very nice. That's, I think, a very good example of this approach of f of x equals 0. Some people may say, well, you can also use the dynamics sometimes. It's true. Some people do that a lot. They do use the dynamics. They integrate the flow, and then they prove existence of orbits using Poincaré sections and so on. Well, we take a different approach, which is really more functional analytic. But that's an example where this is very useful, because then we forget about the outside world. We just plug a Fourier series in there, and then we apply the same technique. And
where do you get the initial guess for this?
So there's a kind of a bifurcation analysis that is done, that we did, and then we did the continuation. And each of these branch, we have one branch, but there is, because of rescaling, there's infinitely many other branches that are related to that one. So basically, because of that, and we have, out of this one, there's infinitely many other solutions that follow from this. Yeah, but if you take this guy here, then there is a rescaling in the Boussinesq equation that gives me another periodic orbit somewhere else at a different parameter value. It's like if one branch gives me infinitely many other branches. So that's kind of that's neat, because that's a lot of solutions. And if you extend it, because that's periodic both in time and in space, then this is what you see. So then you kind of get, you get you get the idea that it's kind of water waves, and then the amplitude here is pretty large. It's about 40, the amplitude, so that's a very large, that's a very large wave. And the C0 bound is 10 to the minus 11. And again, same ideas, projection, Newton, radii polynomials, and invert numerically defined with that one, an approximate inverse posed on the infinite dimensional space, and then you hope for the best. And if it doesn't work, well, often what you do is that you can increase the dimension, the projection dimension, or you can play with your weight in the function space. Okay, so now something, I mean, this is getting to the close, I mean, this is getting to, at least as far as I'm concerned, to the forefront of what we can actually do now. So that's kind of the hardest, these are the hardest proofs that we've done up to now, and this is still unpublished. We are writing, we are finishing to write the draft right now, but the proofs, the computer system proofs are done. So this is Navier-Stokes on the 3 torus. So these are so U is the velocity, and P is the pressure, so these are the 2 unknowns. And we have this divergence-free equation here, the incomprehensibility that needs to be satisfied. And so if we look for, okay, this is John Ward with JB and Leonard Van Vliet and my former PhD student Maxime, who is now in Munich. Okay, so the idea here was to use exactly the same idea that I presented for Boussinesq and for Kuramoto. So plug now Fourier series in the 3 dimension of space and in the 1 dimension of time, and then solve for, I mean, now it's a lot of Fourier coefficients. Now we have a 4-dimensional infinite 4D matrix of Fourier coefficients, and that, yeah, that's a lot of data. Okay, but so what we did was just to plug that in Fourier in there and then try and hope for the best. The problem with that approach is that that didn't work because we did not get any nice diagonal dominance. So you see the example that I gave you about using the linear part to get a nice contracting tail, and we basically invert the linear part in Fourier space by hand. And often we just got a nice diagonal dominance. Well, that's not happening here because there is this divergence free. So basically this is kind of mixing everything and we cannot really get the nice diagonal dominance. So what we did for that, we actually talked to the engineers and they actually had tricks for that because it's not only theoretical, the problem, it's also computational. So in order for them to reduce the number of unknowns, they do not solve for the velocity, but they solve for the vorticity. So what they do is that they apply the rotational to the problem. The nice part is that now the pressure disappears, so there's no more pressure to solve for. And now we have a slightly more complicated nonlinear part, but it still remains, that linear part still remains. Okay, so this is basically the partial of the vorticity with respect to t, the Laplacian of the vorticity times the viscosity here. And then the nonlinear terms become a little bit more complicated, but still we can use the fact that we do have a Banach algebra, but now we have a lot of dimensions. We have 4 dimensions in Fourier coefficients. So that also, we ignore this. And basically, at the end of our computer-assisted proof for the vorticity, then we can recover using a theorem. We can recover the velocity and the pressure, and we have rigorous bounds for the allocation. Okay? So I didn't write all of that, but this is the approach that we used. And again, that was thanks to the, so Leonard is really the scientific computing guy on the team, even though JB did the code. But he had all the tricks that the engineers are using, and then if we didn't have that, we would just miserably fail because there was no nice structure to be exploited. And it's a little bit of work to actually go back and say that the computer-assisted proof for the vorticity can give us something about the velocity. So that's also something that we worked on the analysis side. Okay, so that's what Leonard computed. He computed a bifurcation diagram using an external forcing term with a very specific form. So some people in the applied in fluids, they call these kind of forcing terms Taylor-Green flow. So I don't know exactly why it's called Taylor-Green, but that specific forcing term here, when you decrease, okay, so if I didn't have forcing terms, then there would be nothing to prove in terms of non-trivial dynamics, because there are proofs that that's what everyone believes, that it goes to 0, right? So and there are proofs that there's no periodic orbits if there was no forcing term here. So, there's nothing to do in terms of dynamics for that problem. There's a lot of interesting challenges when f is 0, but this is not what I'm talking about today. So when the viscosity goes to 0, then now we go to Euler's equations. We will not be able to use our technique as of now to handle the case nu equals 0 because we need a tail that is contracting, right? So this kind of techniques not working yet for Euler's equation, but I mean it works for Navier-Stokes. So when that decreases, or in other words, when the Reynolds number increases, then bifurcation start appearing. And that green line, which is the same as the red line here, so that's a steady state, which is known exactly because of the shape of the specific forcing term here, which is minus sine x1 cosine x2 divided by 2, cosine x1 sine x2 divided by 2. And the third component of the forcing term is 0. So as I said, so this is known analytically. We have actually formulas for that because of the forcing term. And then what Lennard did was to compute, to realize that there was a Hopf bifurcation there, giving rise to a two-dimensional orbit. So basically, this orbit, this periodic orbit, does not depend on time. I will in fact show it to you. That's the one. Actually, that's the one we proved. But that's a 2D. That's a 2D. And what you see here is the time periodic solution with rigorous upper bound proven. But it does not depend on z. It depends on time and it depends on x and y. And what you see there is the isosurface of the third component of the vorticity. Because then the unknowns, the unknown is the vorticity defined on the fourth torus somehow with values in R3. So in order to visualize that, well, we have to make choices, right? So we took the third component and then, well, it's still defined on the fourth torus. So then we have to visualize it somehow. So we took the isosurface of that of that orbit. So that's what you see here. But that really came out of a Hopf bifurcation. So we are far from the bifurcation. And then, I mean, I don't see any way to actually do anything to get proofs like that using bifurcation theory. Or maybe they could do. It would be possible to really do a bifurcation. But then what we want to do now is to actually prove something here. Because at that point, there is a secondary bifurcation.
What is the meaning between red and green, the sign?
I think that these are there may be two different levels. I actually have to, I think that so when we took the isosurface, it still has value. So I think it's the max and the min value of that, it's a good question, in fact.
This is the graph for the vorticity? Or?
Yeah, this is an isosurface of the third component of the vorticity. Yes. I mean, the color, I could go in the paper now, but let's say right now I don't feel like it. So okay. I can tell you after. Okay, so that's the computer-assisted proof, again, using the same techniques, but for the vorticity formulation. And what we want to, and then that was using how many modes? Yeah, 28,000 modes. So since it does not depend on Z, then we didn't compute anything in Z. We used 17 Fourier modes in space and then 11 in time. And that led, and then we use on top of that some symmetries inherited from the function f into the bifurcation. And so we reduce the dimension by quite a lot, but that still remained to be, to be quite large. And that's what we want to prove now. So we want to prove that that's a really fully state. I mean, now it depends on the three components. So it's similar in spirit, but now you can see that that depends on Z. Okay, so we have all the estimates, in full generality for 3D Navier-Stokes on the three torus, but now it's just a matter of computational time. So basically, the proof of the previous one was done on a laptop, on a MATLAB, using MATLAB and IntLab. So let's say this is, now we are not at all exploiting the full potential of modern computers. So let's say we believe that by rewriting that either in Julia or in C++, and then by using different strategies, we could prove that. And the idea is, if we can succeed in this, and we have to have a general code that would do that, then to move further, for greater Reynolds number, and then try to get computer-assisted proofs in the turbulent regime. And eventually, we want to prove existence of connecting orbits to have eventually proof of turbulence, right? But that's still pretty far, but at least we start getting, I think, some interesting results. Okay, so now I want to talk about one last. Yep.
What's the meaning of here? What kind of secondary bifurcation is?
Pitchfork.
Yeah, a pitchfork.
Yes. And that pitch 4 breaks the symmetry of basically that symmetry, and now it becomes 3D.
So first you have one equilibrium, afterwards you get the half bifurcation
Yep.
using stability, and afterwards you get this pitch for
Yeah.
making it
Yeah, fully three-dimensional.
instead of one, right?
What do you mean one? So I mean this is still two-dimensional. That still depends on x and y. I mean, what do you mean by one?
So pitch
So-
4, what I'm thinking is
Oh yeah, but I mean of course there that continues.
goes up into 3.
Yes, there is. I mean, there is. Let's say. I mean, it's probably it's the period. So we see only one because that's the other guy that is there is under the same branch. But but there's basically the idea is that there is a symmetry breaking bifurcation, and that now leads to the full 3D orbit, and that's really going to be the next paper, because for now that has already been a lot, and then most of the hand waving talk, I mean what I talked about in terms of vorticity and then all the estimates, they're all fully general, but yeah, of course this is a challenging computational problem, but I think it's nice. I'm proud of that. Okay, so my last example that I want to talk about is something completely different. Well, completely different. Not completely different, because it's still using the fact that we can compute using these tricks some solutions. But now I want to combine that. I want to combine rigorous computing with topological method, and in that case it's going to be flow homology. Okay, so why are we interested in making flow homology computable? Well, some people may say it's crazy, because how can you compute ever some flow homology in full totality? You're probably right. But still, there are some potentially some ingredients that we can feed into flow homology if we know the global homology. I will talk about what it means, and then it's still possible to conclude using topology the existence of some connecting orbits or some different type of orbits. So we often call that forcing theorem. So Jay mentioned one of them without mentioning the term forcing theorem, but this blue sky catastrophe, where if you can show the existence of one orbit, then that forces the existence of other type of orbits. So that's kind of nice from our perspective, because once we do a proof, it's not the end of the story. In fact, sometimes we're motivated by using different, more theoretical mathematics, mathematical tools, to actually feed. I mean, to provide the seed of these more general theories or more theoretical theories, and then get nice results about dynamics. Okay. And one thing I want to mention is that, say, 30 years ago, there were people trying to do the same for Conley index. I highly doubt that we'll have the same success that they had. But a while back, Conley index theory was really a generalization of Morse theory, which I'm also going to talk about in order to explain what flow homology is. But some people were trying to make it computable, and that was a little bit, I mean, some people even said that it was controversial. That I remember the story of a student who wanted to go and work with a developer of that IDA, and then people said, "Oh, careful, because that's kind of a controversial field, and to try to really compute these kind of things within a computer." Well, now a lot of people have had success for Conley index, and well, it would be nice if we would at least made similar progress, but now for flow homology. So I will talk about what it is. Again, it will be not a deep introduction to flow homology, but I will describe what are the ingredients to define flow homology. And I will show how to compute some of these ingredients using the tools that we talked about in the last 3 days now, and how we can, combine that with nice topological methods. Okay, so this is joint work with JB, Marcio, and Rob van der Vorst. Rob is really the expert in flow homology. They're both JB and Rob at Vrije Universiteit in Amsterdam, and Marcio is in San Carlos, University of San Paulo at San Carlos. Okay, so in order to talk about flow homology, I have to step back and then to be a little bit more modest and to explain the ideas behind the construction of Morse homology. There are different ways to construct Morse homology, and the one I'm going to present is really the version that Flower, when he proved the Arnold conjecture, used actually to construct its homology. That really is the version. The Morse theoretical version of Witten yeah, I mean, that's really what Flohr took in order to define his Flohr homology. So what is the one construction of the Flohr homology? So in the classical setup, what do we have? We have a manifold, and it is finite dimensional. It's compact Riemannian manifold. And then we have a smooth function, which is called a Morse function, defined there. So on this picture, you could think of the Morse function h as measuring the height of the torus, going from 0 to 1, say. And it has to be smooth enough so that we can think of a flow on that manifold. So we consider now the gradient flow. X dot equals the gradient of h on the manifold. And what you do is that you compute three things to define the Morse homology. First, you compute the critical points. So it's, in that example, it is the critical points are basically steady states of the gradient flow. So there are points where I do not move, or in other words, I do not flow down on the manifold. So in that case, there are 4 of them. So these are the points such that the gradient is 0. Second ingredient, which is needed to define the Morse homology, are the Morse indices. So it's essentially the dimension of the unstable manifold. If you think of a flow on that manifold here, well, there are 2 directions where the solutions are getting out. So that's a 2-dimensional manifold. So the dimension, so the Morse index of that critical point is 2. That one is 1, 1, and 0. So this is the second ingredient. And the third one are the connecting orbits, but not all of them. Because if you look carefully on this, then you'll have infinitely many from the top to the bottom. So what you have to compute, you compute the connecting orbits in order to define the boundary map, but only between critical points which differ by an index, a Morse index 1. So let's say all you need to compute in order to define the complex, okay, well, maybe, yeah, is to compute the number of connecting orbits between this one and this one, between this one and this one, and between 1 and 0. And the rest, you don't even care about that, okay? Then the construction goes as follows. So once you have these 3 ingredients, then you define the chain groups. So in homology, we have to define chain groups. And these are groups which are generated by the critical points. So C2 would be 1-dimensional group. C1 would be generated by these 2 critical points. And C0 would be generated by that critical point. And the boundary map, which I kind of described in some sense, so what does it do? So in order to compute, so I take an element x in C2, say, and in order to get, so that's the boundary map, it goes from ck to ck minus 1. So I'm mapping the group generated by the kth, the critical points of index k to the critical points of index k minus 1. And how do I get that map? What I do is that I count the number of, that's what it means, the number of connecting orbits between x and y for all possible y's in ck minus 1. So for all, that's the for all possible y's such that the Morse index of y equals k minus 1. So I could have more than, I could have 10 elements, 10 critical points in my group, so I could have different connecting orbits. But really all I care about is this minus 1 here. I mean, I could actually write mu y minus mu x equals minus 1. So this minus 1 will actually be very important in order to define the Flohr homology. In fact, that's really the spirit of how to define it. And there's a theorem that says that the square of that boundary operator goes to 0. That's why it's a nice homology. And therefore, we can define the homology groups, which are the kernel of the boundary operator, del k divided by, or mod by the image of del k plus 1. And because of that relationship, then the image of del k plus 1 is included in the kernel. And that's a well-defined group. And these are the homology groups. And a very nice theorem is the following, is that you can actually recover from that homology the homology of the manifold itself. So if you think about having a very high dimensional manifold, it could be, that's classical stuff, but that could be, you could be dealing with extremely complicated stuff here. You could have a 100-dimensional manifold, and all you need to do is to compute 0-dimensional points, which are critical points, and then connecting orbits. So these are 1-dimensional curves on this 100-dimensional manifold. And out of this very low-dimensional information, you can conclude about something very global, which is the global homology of the manifold. So that's why often we hear recurrent saying in topology that that's precisely that part of mathematics which allows going from local to global. So that's a very good example of that statement. Okay, and then in fact, if you want to compute the homology of the torus, well, you can actually do all of what I just said, and you'll recover it. Okay, so I will not describe that because that's not the point. Okay, but that's the classical Morse theory, and then Flow homology took that ideas, and now in the context of strongly indefinite problems, which I will talk about. So let me just recap quickly. So critical points, Morse indices, connecting orbits give Morse homology. Okay, so there's this kind of equality here. So if I want to get the global homology, then I can compute these things, and then as a function of these things, I recover the Morse homology. Well, there are cases where I may know in advance what the global homology is by some continuation property, because as it is the case in many different topological approaches or topological invariants, then the topological invariants, they continue as a function of some parameters. That's the same in Conley index theory. So there are cases where it may be the case that you know the global homology, and you know some critical points and some indices, but you don't know about the connecting orbits. So that's basically what I want to talk about, but now in the context of Flow homology. So if I know the homology, and if I know critical points and Morse indices, can I conclude about connecting orbits? And the answer is yes. In the context of Conley index theory, that answer is provided by the connection matrix. And that's basically the boundary operator because Conley index is a direct generalization of Morse indices. So, I mean, when you have an index for a Morse, you need to have a critical point, right? So that's really an index for a critical point, whereas Conley index theory is the generalization. So instead of being the index of a critical point, it's an index of an invariant set. It could be very complicated. It could be a periodic orbit. It could be something non-gradient, right? Because this is gradient system, and yet you would have the boundary operator, and all of that construction leads to connection matrix. And once you have the connection matrix, you can, if you have enough information, conclude about the existence of connecting orbits, which is, from the perspective of dynamics, sometimes very important. Okay, so that's this idea that I want to exploit now for in the context of Flow homology. So to well define a Flow homology, we have to talk about a lot of different things. We have to talk about compactness of bounded solutions. We have to restrict, in some sense, in the same spirit that what I did with Boussinesq. So we just look for the set of bounded solutions, and in that set we have compactness, and that's allowing the construction of the Flow homology. So Flow homology is really an homology for strongly indefinite problems. What does it mean to be strongly indefinite? It means that if you have, say, a critical point, then you have infinitely many stable eigenvalues and infinitely many unstable eigenvalues. So that's already much harder than when you have a finite dimensional problem where it's always finite. So the Morse index is always defined. I talked already yesterday about the link between delay equations and PDEs. So parabolic PDEs. So for many parabolic PDEs, for instance, you'll have still a finite dimensional unstable manifold, and therefore you still have Morse indices in context of gradient PDEs, dissipative PDEs. So, but then when you do not have finite dimensional unstable manifold, therefore when you cannot really talk about a Morse index in the classical sense, then that calls for an alternative, and that's what. Well, that's what we'll introduce to be relative indices in the context of Flow. Okay, so I want to talk only about one example, okay? And otherwise it's going to be too theoretical, and it's the last talk, so I don't want to kill you guys. But so I want to consider this example here. These are referred to as the Cauchy-Riemann equations, and there's no well-posed initial value problem for this problem. Yes?
Is it an assumption that there is no center manifold in this center directions?
If there is what, sorry?
Center directions.
If there is
You need some assumption of that type.
yeah, we need, it's like in classical Morse theory,
Yeah.
you need this non-degeneracy condition.
Is this something similar here?
Well, in here we'll choose parameters for which is the case, for which we have no center directions. Yeah, that's a good point. But I'm going to sweep a lot of details under the rag. I'm sorry, but yes, you're right. There's some non-degeneracy conditions always, as always. I mean, this is the case for Morse theory as well. Okay, and so if you want to relate, because there's an underlying variational principle here, and then these are the L2 gradient flow of the action functional, which is the following. So, yeah, I mean, in that case, psi of u is just lambda u minus u cube. But that's really, and then that's a gradient flow, and then that gradient flow will have critical points, and these critical points will have infinite dimensional stable and unstable manifold. I will actually talk about that. But since it's a gradient system, then the eigenvalues are real. Okay, that's kind of going to be very useful for us here because of the way that we will actually do the computer-assisted proofs and really control the spectral flow. Okay, so that's important for us. I mean, if they're not real, then there could be something done, but it's going to be useful, say. Okay, and well, if you want to understand the ill-posedness, you can actually look at the linearized operator. Okay, by looking at when you have a critical point, you have this, and that leads really to infinitely many stable and unstable eigenvalues. I will actually show in some specific case where we have a domain, a bounded domain, like between 0 and 2 pi, I will show you the eigenvalues. Okay, so as I said, the fact that there are infinitely many positive and negative real eigenvalues, unbounded in both directions on the real line, calls for a different type of index. Okay, and now I want to go back to Morse, and I want to emphasize the important ingredient in the connecting orbits. I mean, what kind of specific, what does it mean to actually compute with the relative index with the difference by 1, right? So if you look at the spectrum of the derivative of, I mean, that's the second derivative, so that's the Hessian matrix here. So there, at the top, I will have 2 unstable eigenvalues. And as I flow down, or if you may think of as I move along the connecting orbit from x1 to x2, say, then if I follow the spectral flow, there is one crossing. There's only one crossing. Okay? So that leads to the notion of a spectral flow. And so when there is one crossing, or there could be 2 crossing, or 4 crossing, and so on, then that's the idea of what we call a spectral flow. So here you can see that if you would go from x1 to x4, then you would have 2 crossings. And from the definition of the Morse homology, then we don't care about these. So what we really care about is when there's only one crossing. Okay, that's when there is one crossing. That's where we have to take care of or to take care of the connecting orbits. Okay, so how do we define more generally the spectral flow? So that's the number of eigenvalues which cross 0, and the counting is done so that if I go from the right to the left, then it becomes a -1. Okay. So if I look here, and then the relative index, so the alternative which is necessary to define flow homology, is now going to be exactly equal to the spectral flow. So that's what the relative index is. That's how it's defined. So in that case, the relative index of x1, x2 is equal to -1. So we must first have two critical points. And even though if one critical point may have an infinite dimensional unstable manifold and the other one may have also an infinite dimensional manifold, you cannot subtract the dimension, but you can still keep track of how many crossings. And the idea of Flower was precisely to say, well, I'm going to do exactly the same as Morse, but now I'm only going to count the number of connecting orbits which have relative index -1. Okay? So from our perspective, well, that's nice, but from our perspective, we know how to compute critical points of these kind of problems because this is, again, an infinite dimensional problem. We have some boundary conditions which allow us to use Fourier. So using the same techniques, I can compute rigorously the critical points. Okay? After that, we have method, and I will describe that a little bit. That's pretty cute, how to compute the relative indices. And with that information and the fact that for this problem, we know the global index, we'll be able to conclude and have proofs of connecting orbits for a strongly indefinite problem, which is, I don't think it's trivial at all. So I think even though if the example is simple, I think it could potentially lead to more non-trivial applications. Okay, so the relative index in that case, as I said, you could have infinitely many stable and unstable eigenvalues, and then all you care is you look at the crossings, and in that case, since you have 4 crossing, -1 plus 1 plus 1 plus 1, well, you add them up, and now in that case, the relative indices would be +2. Okay, that's okay. So now let's go back to Cauchy-Riemann. Let's compute the critical points rigorously using the techniques you're now becoming experts in, and as well as the relative indices. Okay, so the critical point, they satisfy this boundary value problem. So we plug Fourier, get to solve. Okay, so in that case, there are some bifurcations, and at lambda equals 6, well, that's where we'll do our proof. Well, that's the thing, right? I don't want to be here. I don't want to have a center manifold. So we are here, and then we're going to prove the existence of these 4 points. They're related by symmetry, so really all I need to do is to prove these 2 solutions and to compute their relative indices of all all of them. So now this is standard. I plug Fourier series. I get to solve that map on an infinite dimensional Banach space, and then I solve that problem using rigorous computing. I'm going to fly over that. And well, we did that a long time ago, but now we did L nu 1, but we did use the weighted L infinity at that time because that's a very old project, which is still not completely written down, but we're getting there. And in that case, well, the derivative, the approximate inverse is a finite dimensional derivative, and these guys, the lambda k inverse, are given here. And this is where you see that you have infinitely many positive and negative eigenvalues. So if you look for the eigenvalues here, they're real, and they are they accumulate. I mean, they go to infinity on both directions. And okay, as usual, then I consider an approximate of A, an approximate inverse, and in fact, this is going to be useful, that aspect here, because we're going to use the approximate derivative to rigorously control the spectrum of the critical points. And that's how we're going to compute the relative indices. So this A-dagger business here is actually very important for the rigorous proofs of the relative indices. Okay? So that's our tool. Okay? The good old Newton-Kantorowicz type argument. And with that, we did the proofs here with error bounds 10 to the minus 13. Okay, so I'm almost done. Because we're all tired, and it's 6 now. So now once I have the critical points, I know them. I know that they are in some small little balls, right, of radius 10 to the minus 13 in some Banach space. So how do I construct and how do I control the spectrum? So I know from the radial polynomial proof that this is actually strictly less than 1. And not only this, as Jay just mentioned in this previous slide, z of r is less than 1 as a byproduct of the fact that p of r is less than 0. Okay, which means that this is the derivative of the Newton-like operator which we used in the proof of the critical points, and we know that the soup over the ball is strictly less than 1. Now we're going to use that. So now I'm going to consider a homotopy path between the real derivative at the critical point, that I don't know exactly, but I know quite well, and the approximate derivative. And because of the fact that I did the proof, what do I get? So for all s between 0 and 1, then we can show that this is a path of non-singular operators by showing that the norm, I mean, that would be the operator norm here. If I decompose things, I mean, I kind of put the s on the left, and then so I will have s times I minus a dagger. We know this is less than 1. And on the right, I'll have 1 minus s I minus a df of x bar. I know this is also less than 1, so this is less than s plus 1 minus s. This is 1. And now I'm using the fact that I have only real eigenvalues. So basically, if that's a path of non-singular, I mean, if I have that this is always less than 1, because of the shape of A, I can conclude that A is actually a bijection. So that must be also invertible, sorry. And now I cannot have any crossing because all the eigenvalues are real. If I had possibly complex eigenvalues, I could have a crossing in the complex plane, so I would have to do something different here. But in that case, since this is less than 1, that's always invertible, and because there are no complex eigenvalues, if it was non-invertible for some s, I would have to have a 0 eigenvalue, but that's not the case. So it's always less than 1, so that means that there are no crossing along that path. So the hyperbolicity of A dagger and df of x tilde are the same. Okay? So what we do is that A dagger is a finite dimensional matrix, and the tail we know what it is. So the finite dimensional matrix, we use the tricks from, we can use the intlab verify eig, which give us really the rigorous location of the eigenvalues, and the tail we know exactly what it is because the tail is here, right? It's here. Yeah, that's the tail. So we know exactly what are the eigenvalues. Okay, so it means that we control the spectrum of df of x tilde. Now, I want to be able to, oh yeah, that's what I said. So that's the spectrum of A dagger. I control that using rigorous computing. That's the spectrum of df of x tilde. As I move, there's no crossing, so therefore I know how to control the spectrum of df of x tilde. That's one thing. Now I want to use that information to compute rigorously the relative indices. Okay? So I have a critical point. I proved it using some A dagger 1, say. I know that there's no crossing in here. I did the same here. I computed another critical point. Another critical point with a 2 dagger. I know that there are no crossings in here. And now the idea is that in the proof of that one and in the proof of that one, I use the same tail, which means that the tails are the same. So there's no crossing at infinity. So the tail of these A dagger, they're the same here, so there cannot be any crossing. Now, all I need to do to compute rigorously the relative indices are to count the difference between the eigenvalues, the positive eigenvalues. Yeah, so the spectral flow is the difference of the positive eigenvalue, and that's a proof. That is really coming from the fact that we did use the radial or the contraction mapping, and we had this A dagger. So I think it is a nice application because as a byproduct of what we did already, we can get more information, and not only we can get the relative indices, but now I'm going to show. No, so that's a theorem. So that's my theorem. So then we computed all the relative indices, and then basically between 0 and x1, then this is -1. Between x2 and x3, it is -1, and so on. So we just computed the relative indices of relative index -1. And because between 0 and x4, that would be 2, but we don't care about that for flow homology. But then we can still write it down. And finally, so now I'm going back to the flow homology a la Morse. So the same definition, exactly the same. Now the only difference here is that instead of having mu x minus 1 equals mu y, then I cannot, that would be infinity equals infinity minus 1 in that case. Well, all I have to do now is to replace that by the fact that I only count the number of connecting orbits that x goes into, and with only one crossing. So only one, so their relative index is -1. And the flow homology is given in terms of, again, the same idea. Okay, so that means that if I want the flow homology, I compute all of these ingredients, and I can get it. Now, in some cases, we may know what it is. We may know because of the continuation process. And then if we have critical points in relative indices, now can we conclude about connecting orbits? And this is the application that we'll talk about. So here's a theorem. At lambda equals 6, the Cauchy-Riemann equation has at least 4 connecting orbits. 2 of them are given by, so there is a proof that there is a connecting orbit between 0 and x1 and between 0 and x2. And as of now, we do not have a proof that, I mean, we have 2 others, but we don't know exactly if this is this one or this one or this one and this one. This is typical from topological, arguments based, say, on Conley index, where you have the connection matrix. So you have a 1 somewhere in the matrix, which says that there must be some connecting orbits. But sometimes it's not possible to put 1 there or 1 there in the matrix, and that means that you cannot, you know that if it's not there, it's there, or if it's not there, it's there. So basically, because of that construction, we can just partially conclude. Okay, but now the idea is that we would like to maybe compute more and then try to rule out that this is not this one, but it is this one. But anyway, so that's the theorem. So now with these ingredients, then we can use rigorous computing to prove existence of connecting orbit in a strongly indefinite problem. And I think that using other tools from rigorous computing, that would be quite tough. But I mean, as of now, this is so new that I don't know all of the tricks yet. But okay, so that's the theorem, and I like it. Okay, so thank you very much.
So any questions for Jean Philippe? In the previous slide,
Yes.
Well, do you need to know any information when your lambda is equal to 6?
Yep.
Do you need any information in the boundary?
No, we don't need, but what we need in that case is that we need this continuation principle. The reason why we know the global homology there is that we know the global homology of 0, and then it continues, so we have the global homology which continues. So that's really what we need to know at lambda equals 6, the flow homology. So that's really we're using, yeah, we are using
you need to prove, how do you prove that there are other solutions?
A very good point. In that case, we know because there are proof that there is no secondary bifurcation and there's no turning back. So here, in general, we would not know that we have all of them. So we would have to basically get a global bound for where all the solutions must exist. After that, we do all our tricks to prove as many as we can, and we have to show there's no other orbit steady states.
So you need some bounds in a boundary, right?
We need to know all of them. Yes, or we need to, we need, in a given region, we need to know that we have everything.
So final question. Do they
Yes.
need to be done by hand, or can be
Oh,
also?
no, you could do, you could do it by hand, or you could, both,
With
right?
the-
Yeah. I like to compute, you like by hand.
No.
We can be friends. We can be friends.
So this can be used for something like critical points of the Lagrange. I mean, it's in some. This problem is a PDE, right? I mean, the Cauchy-Riemann equation has another derivative. There's an x and y.
Yeah.
But could you do something like that for the action of some, the action of some Lagrange?
Yeah. So.
Look for the critical point.
Well, to look for the critical points, definitely.
Probably,
Yeah. I mean, the techniques we have seen up to now. So when Jay started, the first slide of this week's was f of x equals 0. So there's so many problems in variational problems where you actually look for the zeros of an action functional or of some operator in function space. So as long as we have enough possibilities, I mean, as long as the domains are not too crazy, or then we can use some nice numerical methods, then there's quite a lot of hope that can be done, at least for the critical points. I mean, for the floor, then you need enough variational structure to give rise to floor homology. So that has this in this example. But in general, I mean, not all variational problems give rise to floor, but.
Okay, so if there are no other questions, let's thank Jean Philippe and Jay too for the great work. Vamos a poner el material del curso en la página de internet, entonces también van a estar los videos que nos hace el favor de proveer Ciencias TV. Entonces, pues muchas gracias a todos. Hasta la próxima.
Y el examen.
The exam is next Monday.
Gracias.
Thank you so much for everything. Have a safe week. Thank you for everything. Thank you.